Okay. Okay, Ravi, you're on.
Sure. Good afternoon, everyone, and welcome to the third day of the second international symposium organized by the Amex Dart Lab, along with the Robert Bot Center for Data Science and AI. I'm sure you have been having a fantastic 2 days of talks. And so one thing which you would have noticed across these 2 days is that the areas that we covered, even though there was this singular theme of decision making and risk that was running across, right? The speakers are from very different research disciplines, right? And some were from academia, some were from the health sciences, right? Some are from applied researchers, right? And it's going to continue today. The theme will continue today as well. And this is something that is pretty unique to both the RBC DSI group as well as the DART group at IIT Madras. If you look at our faculty and the research that is going on in both these groups, you'll find that the research cuts across multiple disciplines, and even individual projects have PIs from various disciplines, and the strong interdisciplinarity, right, that we bring to the research is the strength of both the centers and as well as the talk that you're seeing in this symposium. So I'll hand over to my colleague Nandan for taking over the proceedings for the day.
Thank you, Ravi. So today we have two eminent speakers, and I'll briefly introduce Dr. D. Shu. Dr. D. Shu is the Vice President and Head of AI Labs and AI Governance at American Express. He's based out of New York. He currently also chairs the Model Risk Committee at American Express. So he has been with American Express since 2001 in positions of increasing responsibility in data science, including acquisitions, underwriting, fraud, customer engagement modeling, and related areas. D and his team are actively exploring cutting-edge machine learning research and its applications in the financial services domain. He earned his doctorate degree in industrial engineering, a Master of Science in statistics, and a bachelor's in engineering in control theory. So over to you, Dr. D.
Thank you, Professor. Okay, so let me share my screen. Let me know if you can see the slides.
Sure. We can see your slides, but now it's in the presentation mode. Great.
Okay.
Thank you.
Great. So first of all, thank you for joining this wonderful conference. So today I will talk about machine learning and deep learning at American Express. To start out, okay, let me reflect upon my own history with Amex. I've been with the company for 20 years. I joined in 2001. I started out as a fraud modeler, right? So at the time, of course, we already had a model. A lot of critical decisions in the company were made with the model, right? But however, the way how the model was developed and deployed at the time was completely different from the way how we are dealing with how we develop the model today. In fact, today, most of our decisions were based on machine learning models, right? This is a significant change from the day when I joined the company, where all the models were based on statistics, kind of a statistical learning model, right? And I think this complete change, right, has largely taken place in the last 10 years. In fact, as I recall, there was no significant change at all in the first 10 years. Things remain kind of pretty much stable from 2000 to 2010, 2011. But however, since 2011, right, the way how we are dealing with analytics in the company, the way how we are building the model, building the decision science as a company have completely changed. I think there are a few factors that contribute to this. Number one, the availability of the data itself, right? It's just exploded in the last 10 years. Number two, the advance in computing, because big data technology is really took off starting from 2010, 2011, right? In fact, the big data labs, which is the predecessor of AI labs today, was founded at that time in 2011, about 10 years ago in the company, right? So number three is really the prevalence of open source software, right? Because the way how the software is written today is completely changed, right? Since my time at the college, right? So and the machine learning is the area where open source, right, has the most significant contribution, right, to the success. And all these three factors, I think, really contribute to some fundamental change, right, in terms of algorithms and theory, right? In fact, machine learning or even deep learning or neural network as a term already existed at the time when I attended college, which is in mid-1990s, right? About 25, 30 years ago. In fact, at the time, I recall neural network was a very popular course at the college. A lot of students, including myself, also choose to take that course, right? And also I recall at the time, the dominant algorithm, the architecture about the neural network is feed-forward neural network with backpropagation as a backbone algorithm, right? And those things were invented during 1980s, in early 1990s. Since then, became kind of very popular in the field. But however, in the subsequent 20 years, things didn't really change that much, right? In mid to late 1990s, in early 2000s, things didn't really change. That's so-called the period of AI winter, right? A lot of things didn't advance. But however, suddenly, a lot of innovation happened, okay? Things 2010, 2011, okay? Including all these very sophisticated deep learning algorithm theory, very novel and very powerful deep learning architecture. All those things happened in the last 10 years, right? I think this is really because of those three things, three factors: the availability of the data, the open source, right? And the advanced computing. All these things have accelerated the development of a machine learning and deep learning as a field, okay? So I just start out as my own reflection upon the history of machine learning, deep learning. And in today's talk, right, first I will give an overview of American Express and the adoption of machine learning at the company. And then I will focus on deep learning. I will introduce a few specific use cases of deep learning in the company. Okay. So first, let me give a quick introduction about American Express. I think everyone heard about the name, right? American Express. It's a global brand in the payment industry, and we have a total of 63,000 employees. In fact, a lot of them are in India. I think a lot of talents in India have contributed to the success of the company. Globally, we have more than 100 million cards in force. Annual revenue exceeds $36 billion, right? And the total billed business, or the total spend flowing through our network, is more than $1 trillion. Okay, so I lead the AI capability, the enterprise AI capability in the company, and I'm part of the global decision science team in the company, right? And we have more than 500 wonderful data scientists and modelers that either masters or PhD. Okay, and what they are doing on a day-to-day basis include build the best possible machine learning models, right? Create very powerful data products and develop new algorithms, new capabilities, right? And then they also spend a lot of time trying to find insights from the data, create very powerful, very effective features used in the machine learning model, right? They're also doing a lot of research, trying to create powerful algorithms and methods. So lastly and not leastly, we are working in a very dynamic, fast-changing, very collaborative, very collegial environment, right? And trying to come up with the best possible modeling solution, machine learning solution to address our business challenges. Okay. On this page, I will describe a little bit about our business model. Okay. As you know, we are a payment company, right? And we are operating as sometimes people call it, as a two-sided market. This is really the essence about our integrated network, right? In terms of two-sided, on this page, as you can see, on the left-hand side, right, this is on the buyer side, meaning we have direct interaction with our customers, with our card members. We manage them directly, okay? So for example, if our card members want to purchase some goods, right, from the merchants first, right, we will authorize the charge, okay, of that purchase, okay? With that, our customers will get the goods, right, from the merchants, right? And then they will make a payment of the equivalent amount of the money to American Express by the end of the month, right, by the end of the month. Or if they cannot make the full payment, and then they will carry forward the balance with interest accrued on that balance, right? Because we manage our customers directly so that we can observe all the data, right? All the purchase data, all the customer activities and the behaviors through these interactions. On the right-hand side, this is the seller side, right? To continue on the earlier example, after the customer gets goods, right? The seller delivers the goods, and then the seller, the merchant, right, will kind of submit the record of charge, right, to American Express, oftentimes on the same day. For most of the large merchants on the same day. For the smaller, medium merchants, sometimes the next day, right? And then after Amex received that record charge, and then we will make a payment to the seller the next day, right? So through this interaction, American Express manage our merchants directly so that we have all the detailed, precise information about merchants, right? So this is what we call global integrated network. On the left-hand side, we are functioning similar to most of the banks that are doing, for example, Chase, Citi, HSBC, right? They manage their customers. However, they do not have direct connection with merchants. On the right-hand side, right, the relationship with our merchants, we are functioning similar to those payment networks such as Visa, MasterCard, right? But however, they do not manage the customers directly. They have all the information about merchants, but they do not manage customers directly. American Express is the only company that manage both customers and merchants, right? At the same time, okay? And this is a very unique business model. And we believe this model, right, gives us a very significant advantage in terms of acquisition of all the data, right? All the data. Because between all these interactions with customers and with merchants, we are getting huge amount of data, right? So this is in fact, I feel this is the most important assets to a company, the data, right? Flowing through a network is more than $1 trillion build business to spend in a year, which involves more than 8 billion decisions or 8 billion transactions. And for every single transaction, it's completed within 10 milliseconds. Okay, and within these 10 milliseconds, an awful lot of things happen. In fact, many machine learning models running at the back end, trying to enable that decision, right? They're all executed in the real time, make the decision, and send the decision back to the merchant, right? Okay. So on this page, this is really about the most important assets, right, in the company, the data, which really powers a lot of our machine learning decisions. And what type of data do we have, right? In terms of the internal data, as you can imagine, we have a lot of customer profile data in terms of spend activity, payment activity, the basic profiles such as like income, wealth, affluence, et cetera, right? Product information is also very important. For example, how many rewards the customer has reaped, right? From their spend activity, how do they redeem their rewards, right? All this kind of product rewards information contain a lot of insights that can help us with a subsequent decision, right? Amex closed loop, right? The global integrated network I described earlier, sometimes called closed loop, right? This closed loop data, in fact, is very important, whether it's for our risk decision or for our marketing decision, especially for fraud control. This closed loop data plays a very, very critical role. For example, if we observe someone, right, the spend activity significantly ramped up at the merchant he's never visited before, that's a very like a high risk signal from fraud control perspective, right? This is just a simple example, and we have thousands of features created, right, in a similar approach by leveraging the power of the closed loop data. Okay, and then for every transaction, right, we can also tell whether the transaction is for the personal consumption purpose or for the business purpose, et cetera, right? This is just a few examples, right, that I want to highlight, right, in terms of data that we have in our system and how it can be leveraged in our decision. On the external side, right, of course, as you know, we every bank using the credit bureau information, right, and trying to understand consumers' activities on, right, on the credit card or other loans outside of, let's say, American Express in this case, right? And also increasingly, we started using a lot of alternative data. For example, like a verified income, the value of that home, the non-traditional loans, right? Usually not reported by the credit bureau, etc., right? And also we started using a lot of bank-related data, bank statements, etc. Okay. Okay. With data-based decision and with model-based decision, right? We feel that's a fundamental reason why we have industry-leading credit risk and the fraud risk results. On this page, right on the left-hand side, this is the chart comparing the credit write-off between American Express and our competition. On the right-hand side, this is the fraud write-off comparing American Express versus our competition. The three payment network, right? Visa, MasterCard, and Discover. And as you can see, for both credit and the fraud, right? Our write-off results is half of the industry, okay? And we think one of the most important reasons that contribute to this result is really based on, right, our institutional knowledge about the data, about the machine learning decisions, right, that leverage those data, okay? Okay, this page is about I think the most important machine learning algorithm, at least in our company, right? The GBM, the gradient boosting machine, okay? I think as of now, probably most people familiar with machine learning must know about this algorithm, right? This probably is the most powerful algorithm for any structured data problem. Structured data, meaning any data that you can represent as a square, as a matrix, right? You have columns, you have rows, right? This type of data, right? The most effective algorithm behind it is the GBM algorithm, okay? And also GBM is the winning solution, okay? For the winning algorithm, okay? For Kaggle competition, as long as the competition is about a structural problem, usually for the winning solution, the GBM is the algorithm under the hood. Okay, and in our company, we have transformed most of our models, okay, with GBM solution in the last 5-6 years. In fact, this is the history about how we apply GBM in our company. I just use fraud as an example. 2014 is a watershed moment, right, for American Express in terms of how we transform our decision, our model decision, right? We started evaluating various machine learning algorithms from 2011, 2012 onwards, and we have made a lot of organized efforts trying to understand what is the most optimal, most suitable algorithm for our decisions as a company, right? And then it turns out, okay, GBM outperforms all the other algorithms, right, by a large margin in a very consistent way with respect to almost all the use cases in the company, okay? So we invested a lot going through that analytical exercise, and we made that conclusion. Okay, that's the time we started, in fact, investing a lot, trying to make it happen, right? In terms of real-time decision in production, right? In the early days, there's no open source solution with respect to GBM type of algorithm. At least there's no open source solution that can run at the industrial scale. So we invest a lot and we developed our own in-house solution that can support the large scale real-time decision in the company, okay? And then May 2014 is the time when we deployed our first GBM model, okay, for fraud decision. And then what we have observed is as soon as the GBM model was deployed overnight, right, the ability for us to identify fraudulent transaction just increased by 30% immediately. This is quite remarkable given all the input information didn't change. They remain as is. The only difference is we replace the traditional statistical model with a GBM model. Then the ability of identifying the risk signals, the fraudulent transactions, right? Suddenly increased by 30%. This is a very, very, I feel, is a monumental moment for us. And since then, this is the data up to 2019, right? Things that we have many, many different versions of GBM model, right? And every version, right? We have created the new features, more powerful features, right? Trying to be part of the GBM model, okay? And I think there are two messages from this page, okay? The message number one, I think the machine learning algorithm, in this case, the GBM, is really important in terms of enhance the efficiency of the decision, right? Enhance the efficiency of the decision. This is especially important at the very beginning, right? If we can identify the right algorithm, the right approach, right? That will give us a head start in terms of leading the competition, okay? But however, the machine learning algorithm, right? Over the time will become a commodity, especially with open source, right? Every player in the field, at least in financial institutions, they have access to essentially the same algorithm. They may be lagging behind in terms of when they deploy the solution, but over the time, right, the solution will converge. And then what really would differentiate between us versus competition is really our understanding about the data. Here, in fact, for every evolution of the model, right, the most critical component is really the data behind it. Every time we want to deploy a new model, we want to make sure we can capture, right, those emerging signals in the data, or we can bring in the additional new data sources that can help create more insights that we can leverage in the machine learning model, right? I think in the long run, the data, right? How do we organize the data? How do we store the data? How do we extract the insights and signals from the data and use it in the machine learning model, right? That becomes very, very critical. That probably is a differentiating value in the long run, okay? So this page shows the history of machine learning transformation in the company. On the top, these are all the different machine learning algorithms that we have explored for the different purposes, okay? Including gradient boosting, machine gradient boosting trees, KNN collaborative filtering, up until today, right? Deep learning is very, very popular. And then on the bottom, these are all the use cases, right, that benefit from machine learning algorithm. In addition to the fraud and the credit model I mentioned earlier, and all the marketing decisions, right? How do we target our prospects, our customers, right? How do we present the offers to them at the right time with the right product, right? In the right channel. Those type of decisions are all powered by machine learning algorithm. And over the time, all these algorithms, right? All these machine learning activities moving to the cloud. And today, a lot of the models, right? Those large scale model activity happening in the cloud, Okay, okay. Now let's move on to the next section. I will use some specific use cases to describe how the deep learning, right, is used for some of the decisions in the company. Because the deep learning is, I think, the most active area within machine learning. So that's why I just want to focus on deep learning specifically in my second section, okay? First, I will describe briefly how the deep learning can even make the credit risk model more powerful. Okay. So on this page, right, the chart on the bottom, this essentially is the representation of how a traditional model is developed. Well, at least the traditional risk model is developed, right? If we want to predict the credit default, right, whether our customer will pay back on their balance, right, whether they will default, right? So the basic process is, first we need to define training data, right? We need to select a month. In this example, February 2017, we select that month, select all the customers from that month, and then we select all the attributes, or the what we call independent variables, right, from these customers in that period, February 2017, right? And then we want to use those variables, right, to predict whether the customer will default or not in the next 18 months. That's a basic configuration of any risk model, right? But as you can imagine, whatever the variables that we use from the months that we select, right, in this case of February 2017, all the variables will also exist, right, in every prior month, right? Like in January 17, December 2016, et cetera, all the way back, right? All the way back. We have the same set of information, right? And of course, this historical information is extremely important in any risk model, right? And we always use the historical information in our decision as well, right? But the way how we leverage this historical information on the longitudinal data is through the creation of the features, For example, we can take, right, our customers' balance today in February 2017 and compare to their payment capacity, payment activity in the past, right, in the last 12 months, right? And then we can create a lot of features with this type of calculation, right? In fact, in that particular example, it's what we call the auto pattern variable, right? We have many auto pattern variables. This is just a small example about the way how historical or the longitudinal data is used in the model is through really the creation of the features, right? Okay. But now the question is there a better way of leveraging longitudinal data, right? With the deep learning, right? We have seen, right? Some of the deep learning architecture, for example, RNN, or the recurrent neural network, is a perfect solution that can help us leverage historical data in a more organic, in a more native way. Or in other words, when predicting risk, we can feed, right, say the complete set of variables from February 2017 into a model. But in the same fashion, we can also feed the same set of attributes from every prior month into the model, right? So this is what we are doing, okay? We use a specific architecture, the gated recurrence unit model, or the GRU model, right? Within the RNN family, we use GRU model to process this type of longitudinal information, right? What GRU does is, first, right, we feed the complete set of variables from the first period to the GRU, okay? And if you are familiar with GRU, there's all the suffix, all the very effective, sophisticated processing mechanism or the encoding mechanism happening in the GRU cell, right? It will output the hidden vector, a hidden state, to the next period. In the next period, right, the second GRU will take the hidden state from the first period and also will take the same set of attributes from the second period, processing it, and propagates right? The next set of information, the next set of hidden states to the subsequent GRU cell. And this process repeats until, right, all the information, okay, is propagated to the very end. And then we have the dense layer to do the final processing before we output, right, the prediction, okay? And then how does it perform, okay? This chart shows essentially the GRU model performance relative to GBM, okay, our backbone algorithm, right? For the different segments of the audience, different segments of the customers, right? And here, within each cluster of the 3 bars, right? The first bar is a performance, by XGBoost, right? The most well-known GBM implementation, right? XGBoost model performance. The second bar is the GRU model performance. Okay, the third bar is the combination of the 2 models, the combination of GBM and the GBM and the GRU model performance, right? As you can see here, the performance of GRU alone already exceeds the performance of XGBoost, which is, in my mind, is quite remarkable because for the type of data that we have, in the structured data space, right? It's very rare you can find anything that can outperform GBM because we have conducted thousands of experiments, right? Very rarely can any algorithm outperform GBM, okay? And this is the first time we can see, right? As a standalone algorithm, it can already outperform, right? Outperform GBM model. But most important is really the combination of the ensemble of the 2 algorithms. They significantly outperform our baseline solution, which is based on the GBM, right? And here the lift you observe, right, in terms of 1%, 2%, or even close to 3% for our charge customer segment, right, is very significant, okay? This number may seem small, right? 1%, 2%, 3%, but however, for us, right, every 1% improvement in model performance means tens of millions of dollars, right, saving in terms of our bottom line, okay? So this is a very, very important for the company. Okay, here I want to share a few insights, okay, with this exercise, okay? Since this is a RNN model, right? GRU is one of the RNN architectures, and the inputs into the RNN type of model is really the sequence of the data, right? As you can imagine, the length of the sequence probably will influence the model outcome one way or another. What we have seen is on this page, yeah, you see 2 charts, right? On the left-hand side, this is essentially the model performance represented by the recall. And on the right-hand side, the same model performance, but represented by Gini. Essentially, they are the same thing, right? They're the same thing. Okay, we see very clearly, okay, as the sequence of length becomes longer and longer, right? The performance also becomes better and better. It doesn't seem at 12 months, the model performance has saturated. So in other words, there's additional benefits if we can make, right, the history even longer, make the sequence of longitudinal even longer, right? But this is not what we have experimented yet, okay? We have experimented up to 12 months, but we can certainly prolong the sequence of the data in order to really take full advantage of the power of the longitudinal data, okay? The second insight is really about data preprocessing. For a lot of machine learning algorithms today, like GBM, XGBoost, random forest, right? This type of decision tree-based algorithm, data preprocessing usually is not really that important because decision tree is quite robust, right? Quite robust. Whether you process the data, you do not process the data, they may not really change the outcome of the performance of the model, right? But for deep learning, for neural network type of model, data preprocessing is extremely critical, extremely critical. And to some sense, okay, the success of any neural network model will largely depend on how we pre-process the data, right? In terms of how we handle the missing value in the variables, how do we do the capping, right, procedure? How do we do the capping procedure? And how do we make the right transformation to reduce the skew in the data before we feed the data to the model, right? Okay, how do we treat categorical variable? Here we use Laplace smoothing technique, right? To make a better representation of categorical variable. Of course, the standard scaling is also extremely important for the success of the neural network model, okay? So here, the message I want to convey is for neural network model, right? Not only the sophistication, the novelty of the architecture and the algorithm will determine the success, but the data preprocessing, that single step, sometimes is as equally important in determining the final success of the model. Okay, the second use case is on how we use deep learning to process document. Okay, as you can imagine, for a company like American Express, right, we have many documents. Okay, for example, some documents are on paper, some documents in electronic formats, right? For example, like bank statements, financial statements, invoices, contracts, receipts, etc., right? So processing documents involves several steps, right? Number one, how do we extract the basic information from the document? And then we're trying to understand this information, right? And the last step is really to make use of the information we extract from the document, right? So document processing today for many companies, even including American Express, is largely manual. It's largely manual because human is just doing exceptional job, right, in processing the document. That's very easy, right? To read the document, extract the information, right? For human, it's very easy, okay? But for computer, right, it's a little challenging. It's a little challenge, right? But however, if we can really automate this document processing step, right? If we really can automate these steps, it will not only significantly enhance our efficiency and the productivity, but more important, right? We can make the document processing more standard, right? And more compliant, okay? And more consistent. Ultimately, it will lead to a better customer experience, okay? And on this page, I show a few use cases in the document processing area, okay, over the last few years, right? For example, like a digital auditor, okay? This is about invoice processing. American Express, every year, right? We use, right, a lot of services, or also we procure a lot of goods, right, from many different suppliers and the service providers, right? And the total amount, in fact, exceeds more than $10 billion in terms of goods that we procured and the service that we used from different suppliers, right? And this digital audit is really about the invoices submitted by the suppliers, right? how do we analyze every line item to make sure every line item is consistent with the goods and the services they actually deliver to American Express, right? Want to make sure we pay the right amount to our suppliers. Do not underpay, but do not overpay either, okay? And how do we automate that process, right?
Dr. D, just a
Yes.
gentle reminder that we might be running out of time. So maybe a 3-minute wrap up so that we just have a few minutes for question and answers as well.
Okay, sounds good. Then let me quickly move to the next page. Okay, this is a specific example about the bank statement verification, right? The basic purpose of this exercise is with this bank statement, this is the cover page of the bank statement, right? And how do you extract the information? How do you extract the information, okay, from this bank statement? For example, what is the name, what is the address, what is the account number, what is the routing number, etc., right? This is a very mundane job for a human, okay? But however, for a computer, in fact, it involves a large set of machine learning algorithms, right? And some of which are deep learning powered. For example, how do you even detect objects on the statement, right? How do you detect objects? In fact, this is a quite sophisticated research topic, right? We use so-called region-based CNN as a first layer, on top of which we overlay with some graph neural network, trying to leverage the neighborhood information in order to isolate those objects in a most effective way, okay? So this is in fact, the last use case I want to cover for today, the NOVA. Okay, NOVA, in fact, is an NLP capability that we have deployed to power our customer services, right? Including the phone IVR, right? How do we really transcribe from the voice to text, right? How do we handle the travel booking? How do we automate the chats with our customers? How do we enable or power the search in our mobile app? And how do we classify emails, right? Before we forward the email to the right department for further processing, right? All these servicing requests, they are very manual today, right? But we can use deep learning to really automate these processes to make it a lot more efficient, okay? On this page, you see the basic process, right? Behind the scene, what happens, okay? This is in fact a chat with our customer. If a customer said, I would like to book a flight ticket, right? This is the utterance from the customer. But at the back end, we have a deep learning model, right? The BERT model, which is very popular in the last couple of years. We have a BERT model for identifying the intent. In this case, we can accurately identify the intent of being travel booking. And then if the customer say, I want to fly from New York to Paris, and that at the back end, we also have another BERT model trying to do the name entity recognition. We can identify, oh, the departure city is New York, and the arrival city is Paris, right? We have about 180 intents. We have about 50 name entity pairs. They are all identified by the deep learning, the BERT model at the back end. And with those, right, if we can identify the intents correctly, if we can identify name entity correctly, and then based on that information, we can design the most optimal customer journey to address the needs from our customers. Okay, this is the last page for this talk, right? How do we bring human in the whole process, okay? Because for NLP task, right, I think the most challenging part is really about the data, right? How do we really label the intents? How do we label the name entity, right? because without these labels, no matter how powerful the algorithm is, it can't really perform, right? We need to have a large amount robust data before we can even develop the powerful deep learning algorithm, right? So to address this, right? So in fact, we have about 15 people team. We call the AI optimization team. Their day-to-day job is really trying to process the data, okay? Trying to do the labeling in a very efficient and accurate manner, okay? And we feel this probably is one of the secret sauce to make deep learning really work for our use cases. And along the way, we also designed the various tools. For example, we customized an open source project called the Label Studio to make, right, this interface for labeling more user-friendly and more efficient, right? More efficient. So what I want to articulate here is machine learning. Machine is important. However, to make machine more powerful, right? Human is the final determining factor, right? Human makes machine more successful. Okay. With that, I think this is the presentation I wanna share with everyone. So I don't know if how much time we still have for the questions.
No, thank you so much, Dr. Lee Su. And I also know that you might have a time constraint. So keeping that in mind, maybe if you just have time for maybe 1 or 2 questions, we would love to hear from you. Let me just pick a question that we've got from the chat, which is, what are some of the challenges you have observed while taking a machine learning model to production?
In terms of challenges, I think at the early days, I think computing is one of the bottlenecks, especially as the algorithm becomes more and more sophisticated, right? We need to rely on more powerful computing infrastructure. I still remember when we want to migrate from a sample of the data to the full population, right? In order to develop a more effective machine learning model, we almost need to shut down the entire cluster, right? Other people cannot work before the model is built, right? This is kind of pain point, okay? But over the time, I think the right solution is really move a lot of those activities to cloud. This is the way how we address the challenge. The other challenge I feel is still an open problem. It's really about the data, right? The success of a model is really depend on the availability of the data, availability of the unbiased representative data. But however, the data that we observe, right? In reality, all the data is censored, right? Unless we conduct large scale random experiments to collect unbiased data. But oftentimes the data in production, right? The most critical data, they are always censored, right? And how do we really conduct a research, right? Trying to understand, right? How we can build the most effective data, even having a bias in the data, okay? A live example is for our credit decision, right? The data can be segmented, right, by the different balance levels, right? As you can imagine, the user balance range from, let's say, 1,000 to a few thousands, or maybe 10,000, 20,000, right? And very rarely will we observe someone's balance reach a very high level, like 50,000, 100,000, 200,000, right? But however, our decision, right, need to make whether you have a balance of a few thousand or you have a very, very high balance. In fact, the most critical decision is really when the balance reaches a very, very high level, right? In that moment, risk management becomes super, super critical, right? How can we even allow some people to spend up to $1 million, $2 million, right? We need to make a very careful assessment with the machine learning model, right? But the challenge is in the data, right? We may not have a very representative sample at such higher level of the balance, because you imagine who are those customers we would even allow them to have a balance of 100,000, 200,000, right? Those customers in the history, right, what we observed, those customers are extremely skewed, only for a very, very affluent, very, very credit-worthy customers, we will allow them to reach that level of the balance. So in other words, our data, right, from risk perspective is very skewed when the balance is very high. But however, the decision is most critical for high balance, right? Then the challenge is with such a biased data, right? How do we really make the model function perfectly when the balance is very high?
No, very
Right?
interesting. Very interesting. So one other very quick question that I had was, it sounds like a lot of your models are predicting default at a future point in time. And this leads to some amount of actionable decisions, especially at the application stage. How does this really work if you have a current customer and there is already a line of credit or there's already some credit dispersed? Is there value in some of these algorithms where the whole process is midstream? And do you even run these algorithms in such contexts?
Okay, I think if I hear you correctly, you're asking, right, there are different milestones in terms of customer life cycle. How do we make the decisions, right? So, yeah. In fact, we have many critical decision points powered by machine learning algorithm. Or in other words, at every decision point, we have a different model, right? When we underwrite the customer, right, trying to decide whether we want to acquire him into our franchise, we have an underwriting model, right? Underwriting model, of course, we have the relevant data for that decision point, because at that time, the customer, the person hasn't become a customer yet, right? We can only rely on the information we have at that point. But after we acquire him as a customer, right, and then we move him to a customer management stage, right? And then we're trying to manage their activities on a day-to-day basis. And then there's a handoff from underwriting decision to the customer management decision, and then a different set of models, right? Will take over. And of course, that model will rely on all the information that we can observe at the time, including the information that we gathered from underwriting stage as well. So I think this process is really the evolving process, right? And we have all the different sets of algorithms, different sets of models for covering the different decisions across customer life cycle.
Understood. That's very interesting. The last question is, what about data privacy? Are you moving towards a federated learning framework, like an open source models, or to address the privacy component?
Yeah, that's a very important question. In terms of data privacy, right? Usually from a modeling perspective, from a machine learning perspective, I feel it's not such a prohibitive requirement, because we usually develop a model, right, in an anonymous manner. We don't really need the PI information in order to develop a model, right? So the usual practice is even we move our activity to the cloud. This is a super sensitive area, right? From InfoSec perspective. How can we move our data, right? Our data, these are all the customer private data, right? How can we move the data to the cloud, right? And we have a very strict procedure, right, in terms of what information we can we can move, what information can not move, right? And in every touch point in the model building activity, the process, right? We usually strip off all the sensitive information, all the PI information, right, before we process the data. Okay, this is number one. Number two, for every modeling exercise before production, right, we have various control points from compliance, from fair lending, and also from public affairs, right? With these control procedures, they will examine, okay, what information we actually use in the model, right? And this is a kind of basic defense we have, right? We only allow, right, those non-controversial information, okay? Those non-controversial information, the variables used in the model, okay, that will not cause any bias, that will not cause any discriminatory treatment. We will only rely on those type of variables.
So an example like location, for instance, would that belong to the set of controversial or non-controversial?
That's a very good question. Location information, yes, it's a little controversial. I can't say it's absolutely controversial. I can't say it's absolutely non-controversial, okay? And depending on the type of decisions you want to make, right? And then for some use cases, we are not using location information. But for other use cases, right? And the standards is a little different, where we can still consider location information. But location information, even we use it, we have a very rigorous control around what type of location information you can use, right? If the location information becomes too granular, right? And to the degree we can even identify such an individual, we cannot use this type of information, this type of location information, right? But of course, like if the location information is as broad as at the state level, at the province level, right? I think that this type of information, of course, we can use in the decision.
Got it.
But even that, I think for credit decision, right? For those decisions that will affect, okay, that will affect customers, we will not use. We're still trying to err on the more conservative side. We are not using location information. But for other decision, for example, like acquisition, right? I will present an offer to our customers, right? This is a much less sensitive type of decision, right? But for that type of decision, the broad level location information can be used. I'm not saying the granular location, regardless of the use cases, we cannot use. Okay, but however, for those less sensitive decisions like creative and offering and marketing, etc., right? And then the broad level location information can still being considered.
Great. No, thank you so much, Dr. D. We've not had a chance for maybe all the questions. I still see one more question maybe in the chat. So if you have the time or others have the time, please do take a look. But I just wanted to take this opportunity to thank you so much for your very insightful talk and all the answers to the questions. Thank you again.
Okay, thank you very much, everybody. Thank you.
Great, great.